The upper respiratory system starts at the nose and ends at the beginning of the trachea. For the nasal cavity, it starts at the external nares, and the air works its way up the nostril, which would be separated by a septum, but it's not shown on this. So anyway, those are the fibrissae that I just drew, and the air being filtered by it. It filters out debris, pollen, dust, anything that you don't want coming into your lungs and making you sick. So then the air works its way up through the meatuses, and those serve to swirl around the air. So over here, in these not the concave parts, but the upper parts that stick out, those are the conchae. We have the superior, the middle, and the inferior conchae. Those have blood vessels that kind of serve to warm the air before or as you breathe it, because you don't want cold air coming into your body. So now that we have that, next is the oral cavity, which mainly serves to keep things out of the airway, such as food and drinks. It does the same thing as the nasal cavity. It breathes. However, it also has other purposes. Here is the hard palate. It's bony. That's bone right there. And it serves more as an aid to mastication, kind of. It helps form the food into a bolus to swallow. And right behind that, we have the soft palate. I'm going to circle that in just a bit. But the soft palate works at the uvula. And unlike the hard palate, it's not bony. So, see, that's right there. That's the soft palate. It's not bony. So when you swallow food, it keeps it from coming up towards the nasal cavity. It keeps it going the right direction. Now, sometimes it doesn't always work. Yep, that's the uvula. It doesn't always work, and that's why sometimes when people laugh, they will have stuff coming out of their nose. And yeah, that's just showing that it keeps food out of your nasal cavity. So anyway, down through the pharynx, we'll talk about those later, but that just shows the correct tube of where you want food to go. Whereas, what that was circled was the epiglottis, and it demonstrates the epiglottis folding down, which also acts as another barrier to keep food, drinks out of the airway, because if that happens, it's very bad. And here's the vocal cords. The upper one would be the false vocal cord, and the bottom one would be the true vocal cord. The true vocal cord is the one that actually aids in voice. That's the one. That is what makes you able to talk. Okay, so now I'm going to show you the tonsils, where they are, what they do, and how they do it. This one right here is the pharyngeal tonsil. It is located at the back of the nasal cavity. Here we have the lingual tonsil at the back of the tongue and the palatine tonsil at the back of the palate. There they are, the arrows. So the tonsils, they serve to filter out the bacteria, the pathogens, through these tonsillar crypts right here that I am highlighting. They trap the pathogens, say what they are, and protect against them. So here is the pharynxes, which is this long tube which goes from the nasal cavity to the pharynx, and here it is being broken up into 3 sections, because it does have 3 sections named after the different parts of where they are. The top one is the nasopharynx and the oropharynx, and then the last one, which is the laryngopharynx. Okay, so now we have a model of a trachea, and right here is the hyoid bone, which breaks when you're suffocated. That's what happens. You could only die if you break it, is what I've been told in anatomy class. Maybe it's true, maybe it's not. Okay, so what's here is the larynx. That's all of it. And it consists of the thyroid cartilage, which is there, which is what is the Adam's apple. It sticks out more on males and females. And right here, it would be the cricoid cartilage, and it's covered in muscle, but above that is the cricoid ligament. And right here would be tracheal cartilages, which is rings. They're different shapes when you break them off. In histology, they would have C shapes, and that's how you identify them. And these would be the primary bronchioles when it first splits off from the trachea. After that, it splits off into the secondary bronchioles and then to the tertiary bronchioles, which would be the colorful parts. You would notice that they're not even amounts of these bronchioles on both sides because the one lung is smaller than the other because of the cardiac notch. But on the end of the tertiary bronchioles would be alveoli. So in histology, from the trachea go the adventitia, submucosa, and mucosa from inner to outer, or from outer to inner. My bad. And then after the tertiary bronchioles would be the alveoli, as I just said. The type 1, the simple squamous, which just acts as a membrane air-blood burial. And then type 2 cells, which create surfactant, which is a liquid that helps them move so they don't stick together. Without this liquid, it would create sickness. It's mostly known in infants as infant respiratory distress syndrome, or IRDS, which is a lack of, or it is surface tension created in the alveoli, which it makes it hard for them to breathe, even painful. It basically is a lack of lung compliance, which goes back to the physical factors influencing pulmonary respiration, as lung compliance is one of them. The other one would be, the other factors is determined by the lumen size of the airways. As the airways constrict, so does the ability to breathe in air. It goes hand in hand. Lung elasticity is one of the last physical factors influencing the pulmonary ventilation, as I said earlier, and it ties into the rest of them. Okay, lastly, in terms of structure and function, we have the lungs, and on the outside is the parietal pleura, and that's basically a membrane that covers the lungs. It's double-folded, and inside it has the parietal fluid, which allows the lungs to move freely without hurting itself. On the outside is the parietal pleura, and on the inside is the visceral pleura. The visceral is closer to the lungs and the organs, and the parietal is closer to the outside of the body. And what I just drew there, that's the cardiac notch. It is basically a tiny cut-up for the heart. In this line, that's the oblique fissure. Above that's the superior lobe, and below that inferior lobe. And the other one's also oblique fissure, then superior, and then inferior fissure. Between those is the superior, middle, and inferior lobe, as I just circled out. And then the bottom is the base of the lung, which also houses the diaphragm. That's what the base of the lung sits on. The lung, quote-unquote, meat itself splits into lobules. Okay, this is the last picture drawing, I promise. However, right now we're going over blood supply to the lungs, which starts at the pulmonary arteries, which are those which bring deoxygenated blood to the lungs to be oxygenated, which happens with pulmonary capillary networks around the alveoli, which isn't shown here, but it would be towards the end of the bronchioles, which is right there. So it brings blood away from the heart, basically. And only through the pulmonary veins, which are the blue ones, bring then oxygenated blood back up to the heart, and that's basically the pulmonary circulation. Next would be the systemic circulation, which brings blood from the lungs to the rest of the body, which happens with bronchial arteries from the aorta, which I think I accidentally cropped the aorta out. Nope, it's right there. It brings oxygenated blood from the aorta, basically, through the capillaries around the conducting passageways of the lungs, supply O2, which supplies O2 to these airways. Next, to the bronchial veins, to the pulmonary veins, which add deoxygenated blood to the oxygenated blood. Okay, once again I lied, but I promise this may or may not be the last drawing thing. Okay, but this is meant to show the pressure relationship in the thoracic cavity, with the pink being the lungs, and the darker pink being the muscles and the diaphragm. And basically this shows a relationship between the diaphragm moving down and inspiration taking place. So only when the diaphragm moves down are the lungs able to fully expand. And when the diaphragm moves back up, the lungs shrink up. So it shows when the surface area of the thoracic cavity increases, so does the lungs. The pressure within the alveoli is called the intrapulmonary pressure, by the way, which is the atmospheric pressure when the phases of inspiration, of expiration between, by the way, not in. Okay, and the intrapleural pressure is the pressure within the pleural cavity. The negative pressure is due to the pressures pulling the lungs away from the thoracic cavity, and the pressure pulling the lungs back towards the thoracic wall, which would be the pleura and the diaphragm, basically. Like, those two work together to basically keep the lungs where they are, which in turn makes it a negative pressure, which allows the lungs to expand when the diaphragm moves downwards, I guess. Anyway, the intercostal muscles, which the arrow is pointing to directly, which is that pink line at the edge of the lungs, those are the accessory muscles that move the ribs up and out when inspiration happens. Without them, if your lungs weren't able to move, basically, they would crack. And pulmonary ventilation, breathing, happens with a change in volume, a change in pressure. The gases flow down the pressure gradient through Boyle's law, which is going to be talked about right now.
Right. Pulmonary volumes and capacities. So the total lung capacity in a male is going to be 6,000 milliliters. First, we're going to start off with tidal volume. Tidal volume is the amount of air you move in or out of your lungs during a single respiratory cycle. It averages about 500 milliliters in both men and females. Then we're going to talk about expiratory reserve capacity. Is the amount of air that you can voluntarily expel at the end of normal, quiet respiratory cycle with the maximum use of accessory muscles. Males can expel about 1,000 milliliters of air, and females 700 milliliters. Then we are going to go to inspiratory reserve volume. Inspiratory reserve volume is the amount of air you can take in, over, and above the tidal volume. Because the lungs of males are larger than those of females, the inspiratory reserve volume in males averages about 330,000, and in females, 1,900. Then we're going to go to vital capacity. Vital capacity is the sum of the tidal volume, the expiratory reserve volume, and the inspiratory reserve volume. It is the maximum amount of air you can move in and out of your respiratory system in a single respiratory cycle. Then we're going to go to the residual volume. Residual volume is the amount of air that remains in your lungs even after maximal exhalation. There's typically about 120 milliliters. It makes about 100 milliliters in females. Most of this residual volume exists because the lungs are held against the thoracic wall, preventing the elastic fibers from contracting further. Then we have the minimal volume. The minimum volume is the amount of air that would remain in your lungs. They were allowed to collapse. The minimal volume ranges from 30 to 120 milliliters. However, even at minimal volume, some air remains in the lungs because the surfactant coating of the alveolar surfaces prevents their collapse. That's it.
Oh, and you got the
Alright.
notability app?
Gas exchange. Properties of gas exchange. We'll start with Dalton's law. Dalton's law is each gas in a mixture exerts its own pressure. So if you have nitrogen and oxygen, they both exert the same amount of pressure, you will get the same amount of pressure in each one combined together. Alright, and then we have Henry's law. Henry's law is the quantity of gas that will dissolve in a liquid depending on the amount of gas present and its solubility coefficient. So Sg solubility equals K, Henry's constant, times Pg partial pressure. So carbon dioxide, if you double the pressure of carbon dioxide, you will have, it'll automatically double the solubility in water. And same, if you double it again, it'll double the solubility in the water.
I think it's 3 exams and a final, but the final's like 30 points.
Transport of respiratory gases by blood. In oxygen transport, there is a fully saturated versus partially saturated hemoglobin, where partially saturated hemoglobin would carry 1, 2, or 3 oxygen molecules on a hemoglobin, which is the iron-carrying particle of blood, whereas a fully saturated hemoglobin would carry 4 oxygen molecules. And the factors that affect hemoglobin saturation: temperature, which would increase the affinity for O2, whereas CO2 levels in blood, when they rise, blood wouldn't want that oxygen anymore. It would hold on to the CO2 and wouldn't let go, basically, whereas if it had the oxygen, it would let go of the oxygen and then go on its way. So CO2 affects the O2 saturation, which impairs the O2 transport. It could cause hypoxia, which is different types, is ischemic, anemic, histotoxic, and hypoxemic, which is carbon monoxide poisoning. There is a safety margin, which is basically the margin of CO2 and oxygen, which you have to stay between to be safe. That's it.
Reflexes of the respiratory system. We have our protective reflexes, also known as pulmonary irritant reflexes. It responds to physical irritation or injury to the respiratory tract. We have vagus to respiratory centers. We have receptors in our nasomucosa, trachea and bronchi, and bronchioles. Our nasomucosa causes us to sneeze, so if you were to inhale dust, cause you to sneeze. Trachea and bronchi, the receptors cause you to cough, so if you were to do the cinnamon challenge, the receptors there would cause you to cough. And then in the bronchioles, if you were to inhale water, it would cause a reflex constriction of bronchioles. Then we have the mechanoreceptor reflexes, also known as your inflation reflexes. This stretches receptors in visceral, pleural, and airways stimulated with lungs inflate, which send inhibitory messages to medullary respiratory centers, which stop inhalation and start exhalation. Lungs deflate, stretch receptors are not active, which cause excitatory messages to the medullary center, which start inhalation again. Then we have our chemoreflexes. Our chemoreflexes respond to changes in pH, PCO2, and PO2. PCO2 in blood increases hypercapnia, which decreases pH of CSF, which stimulate chemoreceptors and increase the rate of depth of inspiration, which makes you hyperventilate to normal PCO2 in the blood. PCO2 in the blood decreases, which is hypocapnia, which increases pH of CSF and stimulates chemoreceptors, which decreases the rate of depth and inspiration, and hypoventilate till normal PCO2 in blood.